Last time we talked about the set operation, and I remember we left one thing which now talk about is called the index set. So I'll begin to finish the index set part. So we already know set was how to do the union intersection between them was a subset. That's very easy, and how to define it by a property. So index set is just a special case of a set defined by a property. So consider a case like A is a repetition of some elements which have maybe they have a regulation like A1, A2, A3, A4, A5, and we can define another set usually called I because index there is begin with I. So I equal to 1, 2, 3, 4, 5, and A equal to A1 AI, and I is belongs the element I belongs to the set I. So here I is the index set. This is the index set, and each of the I here, like 1, 2, 3, 4, 5, they're indexes. We call them indexes. So A can be defined by AI, and I belongs to I, the capital I, which is the index set. So why we want index set? Because we use a nested set. It's a nested set, like set is in the property of another set. And usually we can write this in a more how to say more convenient form or shorter form. Because imagine here's only 5, but if there's 50, we can write AI and I belongs to I. The capital I equals to 1, 2, 3, 4 until 50. And that's very and I think that's very easy to think about, especially with index. Okay. So I'll give one example of the successfully application of the index set, which is the B here. So if we define I, like I is from 1, 2, 3, 4, 5, 6, or whatever, so you can go very long. You can go very long. But we can define 1 over n here. Let's say if I can denote it. Okay. So here we define 1 over n, and n is belong to this set. The set is here. So actually they're in the form of like 1 over 1, 2 over 1, 3 over 1, 4 over 1, and it goes to infinity because we define here like I is infinity. Okay, so that's the idea of how index set is used and why it's special than the common set. And next, perhaps I want to introduce union and intersection of the index set. So index set can also be used for set of sets. So before that, it's a set of element. 1 over n is an element. Here we can also define like it's a set of sets. For example, we can say like z equal to a1, a2, a3, a4, a5, a6, probably longer, but I don't want to write too long. So here, each ai is a set, each ai is a set. So it's actually, if you see some like rigorous set, we can always do a matching between them one by one. Maybe my matching is wrong. 2, 3, 4, 5, 6. Well, what's wrong with that? Oh yeah, this is B, this is C, D, E, F. Yeah. So it gets very oh my god. It's bad writing, but it's like you can always get a one-to-one relationship between them. And the union, what's the union between them? Let's say we define union as we use the quantifier operator. So there exists one I belongs to a set. Set is here. Probably this is just one example, but sometimes I can be anything. It's always a set of index, right? And there exists one I belong to capital I, such that X belongs to AI. So this is I think this is very easy to understand because if there exists, means if there's only one I satisfy. So union is like or. It's a you can view it as an or. So if maybe it's only in one of them, but I count because it's an or relationship. So this is there is this I, but intersection is defined as for all, which means because intersection is defined as if you define over 3 sets and more, that will be the case like it must satisfy for all sets. If one set doesn't satisfy the condition, then it will not be the intersection of all of them. So it's like for all I belong to set I, such that X belong to AI. So maybe you need to understand this later, but you can always think in this way. But typically, this is a hard way to think. This is a hard way to think. But usually we just understand in this way. So this is usually an easier starting. So we can say A1, A2, A3, and AI with I equal to 1, 2, 3, and AI is just the union between them and maybe union with 3. And the intersection is intersection over them. So this is another, I would say, maybe more intuitive thinking, but not rigorous thinking to indicate the intersection union of the index set. And there's some theories regarding that. All of them, you can see there's 4, but they are all called De Morgan's law. They're all De Morgan's law. And you can see the 3 and 4 here. They are just representation of the De Morgan's law. Like if A, B, we use the C, they do the complement and it's equal to AC union with BC. They're just more set. This is over between 2, and this is between a sequence of maybe n sets. So, and here's another typical version of De Morgan's law, which we'll not talk about proof of 3 and 4 because that's very similar to the proof of De Morgan's law between 2 sets. And for more sets, we just need the mathematical induction, which we'll talk about in the next lecture, I promise. So, but we'll give I will give a proof of this one, which is the first, because this form maybe it's the first time you've seen it. So I'll give a proof of them. So let's see what will happen. Okay, so what we prove the equality between these two sets is we want to prove like for all x in this one, and we can find the if and only if relationship for all x in this side, in this set. So x belongs to A minus or the difference between A and the intersection over BI. Then what happens is x belongs to A and x not belongs to them. And remember, like if we say the intersection over index set is for all I, x belong to AI. Oh, it's B here, but it's okay. So it's like for all I, x belong to BI. But if it's not belong to it, then there exists, we just do the negative operation. So there exists I such that I doesn't belong to, I will use B here. So this is also B. So there exists one I such that x not belong to BI. All right, so that's the negative negation of the intersection. So in this case, we can say it's not a case that for I such that x belongs to BI, and it's similar to there exists one I such that x not belong to BI. Okay. So this is and this is like if and only if relationship. And the last step, which is the most important one, I would say, is like we can put there exists I belongs to I to the front, and this is because the associativity, maybe it's called commutativity. Yeah, the commutativity of the logical operators. So we can put it in the front, and under this condition, we have A x belongs to A and x not belong to BI. And this can be viewed as a set difference. So this is the set difference, and there exists is equal to the union of the index set. So there exists I means like if you just reach 1 or at least 1, you survive in this condition. Okay, so yeah, that's almost for last lectures recovered because we don't have much time. Do you have any questions so far? Okay, so yeah, maybe I will just go to today's topic. Okay, let's see. Sure. And I'm gonna talk about partition, relation, and sigma algebra. But maybe I do it wrong. I will first talk about sigma algebra and what's called a power set here. Yeah, power set. So what's a power set? Power set if like it's just like a set of subset, a set of all subset for a certain set. So it may seems like very abstract to understand, but it's pretty easy. Okay, let's see. The power set always defined as PA. If you study the probability, you may understand, well, this is a probability event A. No, it's not. It's defined in this way. So PA is all of the subset such that X is A's subset. So it's a set of sets. And in this way, we can say this is equal because if X belongs to A, if X is a subset of A, then X belongs to the power set of A. So in this case, it's an element and set relationship, and this is a subset relationship. All right. Sorry. So that's the beginning. So we'll see example to help you understand maybe. So if P equal to 1 to 3, and so what is power set? The set 1 to 3. So let's count all of its subset. Empty set is a subset of all sets, so it has so 1, 2, 3, each single element it is, and 1, 2, 1, 3, 2, 3 is 1, 2, 3. Yeah, it is because it's a subset, although it's not a proper subset. And for the empty set is always a set of every set, including empty set, so it has one element here. But for this one, it may be very interesting. What's the power set of root square 3? Some may say, well, it's a single element, but you probably want to add empty set to it as well. And just have a quick notice of here. We use a set of root square 3, not root square 3, because root square 3 itself is not a subset. It's an element, which will write this relationship called belongs to, not a subset. So that's why we you always remember to write, if you want to write a power set, you will include the brackets. Cool. And there's another theorem, very, very similar to what we proved, like the number of rows for a truth table. For like if there's n, I remember it said like if there's n statement form, then how many rows for a truth table is possible? This is the same idea. This is the same idea. So let's first consider this case. How many elements in it? 1, 2, 3. How many elements in it? 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8, right? 2 for 8. This is 0 element for 1. And here has 1 element, and the elements in the power set is 2. So maybe your guess is 2 to the power of n, right? This is a very intuitive guess. And actually we can prove it. We can prove it by the indicator function. Like for example, we say because like every elements in the power set is it's a set of subsets. So we just need to calculate how many subset is in each set. So for each set, for example, you consider there's like A1, A2, A3, 3, 1, and it can be in. If it's in the subset, it's 1 and it's 0. If it's in, it's 1. If it's not, it's 0. If it's in, 1, not 0. So in this case, we can say how many possible cases? There's 2. Just 2, and we just do the multiplication rule. So we get A. Pretty simple. So I think the main idea is just to consider them as a combinatorics problem, and you can solve it. So if there's so another way, I remember another way to write the power set, especially in probabilities, this one. This is the power set. over the sample space. So this is maybe the set A, and it can be write 2 to the power of A because it's just a power. It has 2 to the n elements. So that's another form to indicate it's a power set. All right. Let's see. We already proved this, and we are moving to a corollary. So this is a corollary considered by myself. So it's very usual to think about what's PA, how many elements in it. But what if we have infinite sequence of P? Then what will happen? It's a result that for any set A with m element. So now A has m element inside, and it contains two, and if there's np, which means there's too many layers of power set, and we'll get 2 to the power 2 to the power 2 and then to the 2. And there's n times 2, the power, and m elements. We can look at one example. So what's the power set of empty set? Power set of empty set, we just know there's the power set of empty set is this one, it's the empty set. And what's the power set of this one? It has 2 elements. It has empty set and also the set of empty set. It has 2 elements. So the power set of power set is actually asking how many elements is in the power set of this one. So actually itself is considered here 1, and empty set must be in it. So here's 2, and this element with the bracket 3, this element with the bracket 4. So there are 4 elements, and this formula is actually correct for this one. So let's check. Because there are 4 elements and there's 3 layers, so it's 2 to the power 2 to the power 2 to the power of what? And m here, how many elements is in the empty set? Is 0, so it's 0. So we do the calculation one by one to find out it's just 4 elements in the end. So this is solved. Cool. And let's go to our next page. So there's one, maybe this is a theorem, maybe this is just like a effect, like the power set of empty set is this one, which we already listed here. So yeah, you can prove it. I can give you one direction. We can talk about one direction. It's like for empty set properties, empty set is a subset of empty set. So it must be in the power set, which means, and if we look at the definition of a power set, then empty set belongs to it. Then the set of empty set must be a subset of it. So we proved one direction, which is this set is a subset of this one. So the second way is to prove it's like this set is a subset of this one. So we can prove both of them, then they're equal. So for proving this direction, we just show like every element inside here is an element of here. So every element belongs to the power set of empty set is like a subset of empty set. But because if A doesn't belong to empty set, then there exists a element in A such that X is not belong to the empty set. So what this sentence actually means is that A has to be empty set, or it's like T to the F condition, which is always false. So A is empty set, which means A belongs to this one, because empty set belongs to here, right? Yeah. So that means like we found 4 elements, 4 sets in this one. For every set in this one is a set in this one. So we prove this one and we add them together to find the equal relation. So that's done. All right, and maybe we'll talk about some basic properties of power set. The power set of A union with power set B is a subset of power set of A union with B. But this is not equal. Remember, this is not equal, because if you consider a counterexample, if you say A is 1, 2, and B is 2 and 3, right? Then the union with them doesn't contain the set 1, 2, 3, because it's at most 1, 2, and 2, 3. But this set contains, so it's not equal, but it's just like a subset of it. And other two, you can just read it out. It's very simple. Like this two must be in a power set, and if A is a subset of B, then then the power set of A is a subset of power set of B. Okay. So maybe yeah, I write a proof for the second one. And okay, let's say, so proving this if and only if relationship is usually like you first assume one side is correct. So we first suppose this is correct, then want to prove this. So how to prove this is like for all set X belong to PA, then it's also belong to the power set of B. So you need to do this one. And it's actually simple to do it, because like if X belongs to PA and A is a subset of B, then this is a transition. Or maybe you cannot say transition because you don't know what is transition, which means X belongs to A and A belongs to B, then X must belong to B. So so every set in A is actually in B, so which means like this set. So we proved this relationship, and it's true under it. All right, so we can also assume another way, like first assume this is correct and prove this one, and the proof is right here. So you can read it later if you have time. If you have any question, you can ask for now. And the backward proving is, I think it's not very difficult to think about by yourself, right? Do you have questions? Oh, clear. Cool. Yeah. Actually, you can open your mic, if you like. Yeah. All right. And the next definition is sigma algebra. I would say, when I first studied, I get very confused about what's a sigma algebra, because I think it's very similar to a power set, but it doesn't. So let's first give a definition of the sigma algebra. So the set of subset contained in the set is called sigma algebra. So it's always like if it's in a finite situation, sigma algebra is equal to the power set. If it's not, let's find out later. So I think there's too many different characters to represent this. Maybe you can use the fancy A. This is what my first professor gave me. It's called fancy A. Some call it fancy B. And yeah, some just call it sigma. So there are many characters for it. And it must satisfy three conditions. So power set, there's only one condition. It's a subset of it, but it has three conditions. First, it must have an empty set. Empty set must be in it, so it's easy to understand. And second is called close under complementation. So if A is in it, then the complement of A is also in it. And third one is a little bit hard to understand. It's like called closed under countable unions. But what's countable unions, you may not know about what's countable unions, but it's just like use an index set to denote the union from I equal to 1 to K. So if there's a very long list of set, like A1, A2, A3 to A100, 1000, and it's belong to the power set, belong to the sigma algebra, then what will happen is like the union of A, look at here, I don't write infinite. I write K, and K is in the set of natural numbers union with infinite. So actually, if there's A1, A2, A3, A4, we already know they belongs to the sigma algebra. But yeah, you may say like I equal to 1, 4 union. Definitely it must be. Yeah, it's defined in most books, but I like to use if it's just A1 union with A2, it's also in it. A1 union with 2 and 4 is also in it. So the K here is denoted as like all of the subset from in the set of like 1 to infinite. Any subset union in it is also in it. And it's very easy to prove it from the definition in most of the book. So I just extended it a little bit from the original version. All right, and we can give some facts about sigma algebra. So what can we know about? So first of all, it's like it has 3 definitions to define it, but we can extend it to have more general properties. So remember, it has the closed under complement. So here, empty set, it must be in S. So what's the complement of empty set? It's the S itself. So S is also in the sigma algebra from this fact. Yeah, so it's combined the fact of 1 and 2. And what we combine fact 2 and 3 will be very interesting. So first of all, if there's a list like A1, A2, A3 is belong to sigma algebra here, then A1's complement, A2's complement, and A3 complement, they also belong to the sigma algebra, right? This is from fact 2. This is from the fact 2 above. And we can do the union with them. They are also in it. This is by the property 3. Oh yeah. So you may wonder what this one is. You may wonder what this one is. This one is just like because we know the natural number is not contained infinite. So we just with the infinite means it just go to infinite. All right. Okay. So this is what left now is inside. And we can use the De Morgan's law because remember De Morgan's law applies to all sets. So we add a complement again, and it will be this form. This is the De Morgan's law process. And to simplify this one, by getting 2 layers of complement is no complement. So actually we found out what's that. It means the intersection of many lists of sets is also contained in sigma algebra. So not only union, but the definition contains union because definition need to be precise and concise, but intersection of the list of sets is also contained in it. So it's also called like closed under countable intersections. Cool. And the last one is, well, this is garbage. Empty set and S is called trivial. Oh my God, it has no meaning because we need the other subset to consider to make it meaningful usually. If there's only empty set in itself, it has no value to analysis, but it's called trivial. Yeah, we will not see it later anytime, I think. It's just you will never meet it. Okay, so give some examples of sigma algebra. Uh so the power set is a sigma algebra, definitely, because you can say power set, all of the subset has its complement as a subset, right? And empty set is also a subset. So first 2 properties satisfied, and for the third one, it's like the union of them. But all of the subset, the elements is in the set, so it's also a subset of the original set itself. So every power set is a sigma algebra. That's it. Especially for the finite set, the set with cardinality, which is finite. And yeah. And the second example may be not very easy to understand because it's not finite. It's all real numbers. It's infinite. And if you study math before, it's called uncountable. It's uncountable. And it's include negative infinity and infinity. So the sigma algebra in this case is in the form of this four. And this conclusion, why we can draw this conclusion, because if you just consider one interval AB and its complement must be like negative infinity to A and the union with B to infinity. So it's in the form of them. No, I don't think I write it correct. It must be a union of them, a union of any of those. So that would be correct. I don't know why I write this. This is not the case. A union of them is the right case. Okay. And this fact is from if you study the best integral, you will know it. It's a this is all measurable sets, and all measurable sets is a sigma algebra. And sigma algebra is used in many situations later. So why I want to say that today is because if you study probability, the first lecture is sigma algebra. If you study the best measure theory, the first class is sigma algebra. And maybe I don't know. I never study the abstract algebra. Maybe it doesn't have sigma algebra. I don't know, but it is algebra, so very hard to say. Okay, so this is the power set and sigma algebra. And if you have any question, you can look at the notes and ask questions. But I will go to the next part, which is the relations and partitions. So first of all is ordered pair. Well, ordered pair is just defined by sets. So we studied sets before. We now have more features adding to the set. Remembering like the set doesn't have the order, so AB is equal to BA in the set here. But this is not the case for order pair. Order pair, this is not use a waved bracket over it. It's just use a round bracket. Okay, I don't know what to say, but I say it's round bracket. Okay, and it's defined as the set A and also set A and B in a larger set. So this is how its information is stored in the computer's memory. So AB, it defines a sequence A and then AB. So this is actually in the time sequence A then AB. Okay, so it has order. With the basic property of containment, it also have the order property added to the set. So this is the ordered pair. Maybe we can also say there is like more ordered pair, like ABC. So this is not ordered pair. Maybe we call it ordered triple, but it exists, and this is defined as A, AB, ABC. So it's also in a sequence. If you see round bracket, it always have an order. If you see the waved bracket, it doesn't have an order. So yeah. And so yeah, I think I just illustrated this one. And and how to say AB, how to compare the equivalence is a good question. Like if you say AB, is it equal to BA? Maybe it's not, right? Because in the BA, what's the case of BA? BA is BAB, but AB is AAB, so which is different. The set is different. And we can always use the storage set to compare the ordered pair. So that's it. Okay. And we'll move to the next one. So there's one theorem. The theorem is like if AB equal to CD, then A equal to C and B equal to D. How do you prove it? Well, we see this event only if relationship once again. So we'll first assume this is true and to try to prove this. So this is our first step. And if we assume this is true, then AB equal to AB is equal to CCD because A equal to C and B equal to D. So it's very direct. We can prove it. Okay. And the second one may be a little bit complex. Is first we assume this is true, and then we want to prove this is true. So we are in the different direction. So yeah, let's analyze it. If we say AB equal to CD, then this is by definition we get it. So yeah, so here there's some ways to analyze it. We can say if the set is equal to another set which has two elements, then one by one must be equal. So first we say if AB is equal to C, is it possible? No, because it has two elements, it has one element. So if B equal to C, then A is not in C. If A is in C, then B is not in C. So in every case, AB cannot equal to C. So there's only one probability AB is equal to CD, right? Because if AB is not equal to C, AB is not equal to CD, then there exists one AB that's not in this set, so it's not equal. So AB has to equal CD. And here we also have another consideration. Is like if the set AB is equal to set CD, then there's only two probability for A. A must equal to C or D. And this is in the same reasoning as we studied the larger set before. And so first we assume like A is equal to D, then A must not equal to C. So these two sets are not equal. So the only probability is like A is equal to C and B is equal to D. So we have solved it. We have proved A equal to C and B equal to D. So we are done for this proof. Okay, and this is writing in a formal way, like a formal way for first week learners of the mathematical reasoning. I write this much, but if you study it for 1 year or 2 years, maybe you can just skip it because it's zero. But if you carefully read this later, you'll find errors, and you can tell me about it because this is written by myself and maybe I get errors all the time. Yeah. And this is the end of the proof. Okay. And the corollary is that if an AB equal to BA, if and only if A equal to B. So yeah, if you have interest, if you have time, you can also try to prove this one. But the idea is like, suppose like A is not equal to B, then the element A is not equal to B, so it fails. And if this is the case, then then AB, the set A, AB, this has set B, AB, and if it's not equal, then if it's equal, then A must equal to B for the single element set, and that will lead to A equal to B, which is down. So before partition, there's also another definition called Cartesian product. So Cartesian product, we use the definition of ordered pairs here. So for any two set A and B, the Cartesian product is a set of all ordered pairs with first coordinate in A and second coordinate in B. So this is the formal definition of a Cartesian product. A and B are set. They can be any set. And we say AB. AB is the element. So the element inside the Cartesian product is in the form of an ordered pair AB. And how the AB comes from, how we know what is A, what is B. A is all the elements in A, and B is all the elements in B. So this is how it was defined. All right. Shit. Okay. So I think example is best illustrator of how it definitely looks like. So to say A has two elements, 0, 1, B has 2, 3. Then we can see AB is equal to 0, 2, 0, 3, 1, 2, and 1, 3. And this is we find out all of the, because it's a for all relationship, so we must find out all of the ordered pairs in it. So there's 4. So let's in another way, let's do BA. Then what is BA? BA is first coordinate in B, so 2, 1, 2, 0, 3, 1, 3, 0. Well, is it equal? No, it's not the same because 1, 3 not equal to 3, 1. Order pair with different order is different. So we get one important result. A times B not equal to the Cartesian product of B times A. It's different. So order matters. The order matters here. There are also some theories regarding the Cartesian product. But personally, I would say they're not important, but you better know it. There are 5 properties here. With the last one, I would say it's less useful. It's the least useful one. And maybe I will talk about the most useful one of them is the fourth one. So you say it is said like that. So yeah, I will first talk about 1 and 2. They're in the form of distribution law of the set and logical operators, very similar. So you can see how it get proved here is very similar to what we proved the logical equivalence. But 4 is very different. 4 is unique. So let's see why I say it. It's like so first suppose A1 belongs to PA, B1 belongs to PB. Then the Cartesian product of A1 and B1 is equal to the power set of A with a Cartesian with B. So how to prove it? Because it's not if and only if. We don't have this sign. So we just need to assume this is right and to prove this is right? So that's our strategy, use the direct proof. So yeah, so because so let's see what information we can get here. A1 belongs to PA, okay. B1 belongs to PB. That's all we know. That's all we know. So A1 belongs to PA, then A1 must be a subset of A, and that's the definition. And we can rewrite it as this one. So we'll just prove this one is true. Okay. So, all right. So for all X in A1, Y in B1. So how do you think about it? Maybe you just think about X is in the set A1, Y in the set B1, and A1 and B1, they're set we already know, they're fixed set. And here, this one means X also belong to A and X also belong to B because they're subset relationship. So by the definition of Cartesian product, X, Y, they form if we use the like you can say A1 times B1, then every element in it must have the form X and Y. And this one must be inside A and B. For this reason, we get this one, which implies for all X, Y order pair in A1 times B1, X, Y belongs to A times B. Yeah. So this is just summarize of what we conclude here. And by this relationship, it looks very familiar. We can say it's a subset, which proves this one. And this one is just logically equivalent to this one by different notation system. Okay, so we have done with it. Let's see how much time we have. We have 16 minutes. Okay. So let's talk about partition. If S is any non-empty set, if it's an empty set, then there's no partition, right? Because the definition set already said S is non-empty set, and the partition of X usually denoted by the capital pi. So This letter, well, is in the definition, but I don't think I read it frequently later. And it just vanished in every mathematical book. So it's defined as the AI, a set of subset of S. And there's one condition. Every AI is non-empty. So this is why we say X must be non-empty, because every AI is non-empty. If AI is empty, if S is empty, then AI non-empty is not a subset of it. So it fails to be true all the time. So that's why we say it's non-empty here. Okay, and each AI must satisfy two conditions. First is like the union of all of it is equal to S. And the second one is pairwise disjoint. This is the definition we first see as the pairwise disjoint. We talked about disjoint before, and we mentioned a little bit about pairwise disjoint. And pairwise disjoint is just like you can see here it's not only two, but a lot of set. But for any x not equal to j index, then and AI intersection with AJ is equal to the empty set. So that's its definition. Okay. Let's get some like intuitions for why we always need partition. Intuition is very simple because mathematicians like to classify things. They want to form classes. Like they want to form what is real number, what's not real number, which is called imaginary numbers. And what numbers they're positive, maybe they're zero, maybe they're negative, or in abstract algebra, what's group and what's not group, what's ring, what's not ring, what's semigroup, is a semigroup can be classified into more categories. Yeah, this is always mathematician asks. Also in geometry, we say circle, some shape are circle, some shape are rectangle, some shape are triangle. So it's just like changes all the time. Okay. And usually we'll introduce a useful strategy to do partition is to make one such all elements in a given block share a common feature. Yeah, that's important. So if you want to do a partition that's meaningful, so you want to separate the numbers of positive numbers, they all have common features. They are positive, right? So they can allow the unified treatment, a specific treatment that can be applied to them. For example, positive numbers, they can always find a root square of all numbers, but negative, maybe not in real numbers. In complex number, it is possible. So that's why we need partition. And maybe I forget to talk about it's like yeah. Okay, yeah, each AI is called blocks. I forget to mention this before, but yeah, each AI is called blocks. It's just the name of it. So let's see one example. Partition can have so many different possibilities, and actually the possibility is 2 to the power of n. Maybe not. Maybe not. 2 to the power of n. No. Because it cannot have empty set. So let's see how many possible different partitions can S equal to 1 to 3 make. It's here. So the first one is 1 to 3. And this is a subset, right? This is AI. And AI union is itself and it's just it. So that's correct. 1 to 3 possible. 1, 3, and 2 possible. 2, 3, and 1 possible. 1, 2, 3 possible. But you may say, well, why not make 1, 2, and 3 and empty set? Why this is not true? Well, because that definition says it must be every AI must be non-empty, so that's why it's valid. So it limits the number of partitions. If empty set can be included in, then it can be infinite because you can add one empty set, two empty set, and infinitely many empty set into it to form partition, and that's nonsense because they just have the same meaning. Okay, and after we studied about the partitions, we can view about relations. Yeah, relations. Okay, let's see. So set S is, yeah, there's a question. So set S is simply made up by all sets belong to a partition of S. So set S is simply made up by, yeah, you can always say like you can do a union of all the sets of all the sets in the partition of set S to form S. That's possible because so why this is true is because here. It's because here. Here because if you like do the union of all of the set inside the partition AI, the blocks, and you get S, right? Is that your question? Ah, okay, nice, sure. Okay, so last 10 minutes, let's finish this one with the relation. I don't know if I have time to talk about, but relation is very important. So relation, it's also an abstract idea. Relation on the set S is always defined on the set S. And first, we'll say relation is regarding, yeah, by its name, it's a relationship of every element inside a set S. So we can first form a partition, no, first form a Cartesian product between S. So each element inside is xy, and xy are belong to set S. This is I think this is very easy to understand. And R is a subset of it. So we are just to analyze if xy is in R or xy not in R. So the the general form of xy in R in or not in R is called is defined relation. And there's one way to write about if x is related to R, which means xy is in R. And we can write this form if xy not in R, then we say yeah, we just get this one, writing this one. You may not understand it, I know. It's very abstract, so we'll see examples of it. First universal relation. R is equal to S, Cartesian product with S. Empty relation, so R is empty set. But these two are nonsense. These two is just definition by some very unusual mathematician. They are never used because they're not meaningful at all. Okay, so we can say smaller is a common relation. Smaller. Yeah, you can see it's from elementary school. One is smaller than two. And the smaller is a very common relationship. So, and it's usually using real numbers because maybe complex numbers don't have order, but their modulus have order. Okay, so yeah, usually mostly used in real numbers. And it represents a set of order pairs, A, B, over R. R here is not relation. R here is defined as real numbers, or reals. Okay, so R here is reals. So for AB belongs to the real numbers. And if we can say if AB is belongs to the relationship smaller than A, it's smaller than B, right? So smaller is a relationship. And most of the relationship we talk about is smaller, greater, smaller, equal to, greater, equal to, equal, not equal, something like that. All right, so let's define classifications of relations. Relations is very boring. Yeah, it's very. The first is the most boring one, reflexive relation. It's just like one and one in real numbers. Wow, it's reflective because they're the same. Yeah, it just means that symmetric means if two, we can say, how do you say symmetric? We can give example of equal. Actually, maybe not equal. Maybe, yeah. It just means that for every xy, if x is related to y, then y also related to x. It's like oh yeah, we can have a example of this one. It's like there's many nodes in a graph. If you can go from this one to this one, then you can also go from this one to this one. So this is symmetric. Like you cannot go from this one. Then you can also not going back. There's no rows between the two cities. So that's symmetric, easy to understand. And reflexive is like going from here to itself. It's always possible. So that's the reflexive one. And the transition one is like if you can go from here to here and go from the road can go from the second city to the third city, then you can go from first to third. So that's the transition. It's like transition. So that's why I always talk about, oh sorry. What? So that's why I always talk about the subset relation is a transition because A is a subset of B, which is related, and B is a subset of C, which is related. And then we can find out A is related to C by subset, by the inclusion. So the inclusion is a transition. The fourth one, the fourth one maybe not that important. It's called inverse. It's a type of relation. But what inverse means is, well, it might look like inverse function. It's like suppose there are two relations, R1 and R2, and for sy belongs to S related to Y by R1. If I know if Y related to X by R2, and R1 is called R2 minus 1, R2 is called R1 minus 1. Okay, and that's it. I will show you one example later. So look at yeah, here. S the second example here. So S is all linear people. P is equal to XY. XY belong to S, and X is a parent of Y. And C is like X is a child of Y. So they are inverse relation because P X P Y is if and only if Y P X. Because if you are a parent of another person and another person must be a child of you, right? So this is called inverse relation. And the fifth one is the equivalence relation. So equivalence, although we use this donation, but most common, I would say this is the most common relation in mathematics because it's equal to the equal sign. Equivalence relation. It can be used between set, used between numbers, and used between I would say belongs of the coordinate. It's in the first quadrant, in the second quadrant, in the third quadrant, in the fourth quadrant, and they are all used to equal the equivalence relation. So it's just like every element inside must satisfy reflexive, symmetric, and transitive. Yeah, we might see one example here. So sure. So there's a common children's game. I think you play it before. It's like you play rock, you do scissors and do paper to and scissors win the paper. Rock wins the scissors and paper wins the rock, right? So let's see what's the relationship of the bits. Bits means it beats another. So rock beats scissors, scissors beat paper, paper beats rock. So let's say first is reflexive. Well, not, right? Because you cannot see rock here. So rock is not beats rock. Rock cannot beat rock, so it's not reflexive. And let's say it's symmetric. No, because rock beats scissors, but scissors don't beat rock. So it's not symmetric. It's a transitive. Uh, let's see. Rock beats scissors, right? Rock beats scissors. And scissors beat paper. So if it's transitive, then rock beats paper, but it's just opposite. So it doesn't, it's not transitive. So after it, we can say, well, it's not equivalence. It's not equivalent because it's neither reflexive, symmetric, nor transitive. So maybe this is a bad idea. Let's see another. Yeah, let's see another example. So all animals in zoo. First, suppose like Z is all the set of all animals in the zoo. So X, Y, Z belongs to set Z. Z is the zoo. So they are all maybe each animal inside it. And we first define this wave line means the same species. So let's check if it's the equivalence relation. So X equivalent to X, yeah, because one species can only be, because one animal can only be one species, it cannot be two species. Because if you catch an elephant, and if you ask, well, if you are a lion, maybe it's not impossible. So elephant is always elephant. So X is reflexive. This means reflexive. It's done. Reflexive. And if you say you find two animals, and the first elephant, the second is elephant. And the first is symmetric, right? Because if the first is the same, is the elephant to same as the second one, then the second one must be elephant and the same as the first one. So this means the symmetric is proved. So let's see a transitive. Is transitive possible? Yeah. Because elephant, you find the first equal to the second. First is elephant, the second must be elephant. And the second is elephant. You always find the third is equal to the second one. So so the third is elephant. And the third is equal to the first one because they're all elephant. So in this case, we say, well, it's proved the transitive. And yeah, so we can find out that the same species relationship is both reflexive, symmetric, and transitive. So we call it an equivalence relationship here. Cool. Yeah, maybe I don't have time today, so I will end it here. We talked to the fixed equivalence relation. So the next class I'll begin with the anti-symmetric relation and talk about what's left over. All right. So if you don't have question, I just want to say goodbye to you.